Hello all, welcome to the AI driven perception learning and mapping for drones course. This is the 5th tutorial, which is introduction to Pytorch. Now in the last tutorial we had discussed about different types of deep learning frameworks. We had discussed about tensor manipulation, essentially trying to visualize tensors and see how the reshape could be done, what are the different rank of tensors, etc. And we had also gone over an example to observe the autograd functionality in Pytorch. Now in this particular tutorial we will take one step further, which is essentially now working with neural networks, working with convolutional neural networks for the task of classification. Hence this particular lecture would cover the classification task, which is essentially taking an image and identifying a class to it. We will also see what do we mean by data augmentation, how it could be helped. We will also take a look at data augmentation and see how it could be used for training neural networks for diverse scenarios. We will go over a quick review of different classification datasets, essentially different types of datasets for the task of classification. We will also quickly go over a code demo in Google Colab notebook. This is first we will try to define the operation in Pytorch and essentially using those fundamentals trying to initialize a model in Pytorch and trying to train it for X number of epochs. Okay, so let's start with classification as a task. So let's define a dataset D, which could essentially have the input image as X and the corresponding label as Y, right. So this could essentially be X1, Y1, X2, Y2 and so on for n, for small n, small yn classes, right. Now this is the data set and essentially it is a classification task. So let's assume that X is an image, right. So let's assume that is an image of a cat and the corresponding label to it, which is 0, right. Let's assume X2 is an image of a dog and a corresponding label to it, let's say 1 and so on, right. Now let's assume there are n output classes, or let's assume there are 10 output classes, right. N is 10, so n could be any number, for us it is 10 here. Now we have reviewed different backbones in CNNs. We have reviewed the operations that are used to make the backbone, which is essentially activation functions, pooling operations, convolution layer, max pooling layers and so on, right. So let's assume that we have an input image. The input image is passed into a CNN backbone. The CNN backbone can consist of different operations, right. It could be activation functions, it could be convolutional layers, it could be so on. Now since this is the task of classification, essentially the feature maps that we get from the CNN backbone, we need to flatten this and make it into a vector. Once this is made into a vector, essentially this is the flatten operation. Once we perform a flatten operation, we pass it through fully connected layer, we will call it as FC layer, right. Let us say we have one FC layer, right. Now the output neurons in this FC layer would essentially be n, right, because there are n output classes, for us it is 10 here, so there are 10 output classes, right. Now one small thing that we will also like to check and we will keep in mind, because once we go over the demo we will come back to this again and check it once more, right. Now we know that in Pytorch the shape is always in this format, which is batch size, the channel, height, width. Let us say we are taking an MNIST data set, the height width would be 28 cross 28, right, or 32 cross 32, right. And the channels is essentially, if it is a grayscale image it would be 1, and if it is an RGB image it could be 3, if it is a SAR image it could be 4, you know, depending upon the modalities. Let us keep it simple here. So which is an RGB image. B is the batch size, it is the batch size that we define, right. Now as it keeps propagating throughout the layer, the output essentially would have a batch size of n. the output layer essentially would have the shape as batch size cross n, n for us is 10 here, right. Now let us do a quick comparison and then we will try to come back to this later on when we are defining the models. Let us observe the predicted value, which is essentially the output prediction, right, and let us compare it with the ground truth. Now when we are observing the ground truth, it is essentially just a number, right, it is essentially a label which is 0 1. So when we are using it to train the model, essentially the dimension of the ground truth would be batch size comma 1, right. Now when we are looking at predictions, the dimension is batch size comma n, right, and hence we use an argmax operator across the axis 1, right, batch size comma n. Essentially this operation converts the dimension or the shape of batch size cross n into only batch size cross 1, and now we can compare the ground truth in this, and we will look into in the subsequent slides we will actually focus more on how this operation can be done. We will come back to this, but this is just to give a basic intuition, right. Okay. Now what is let us come to data augmentation. Data augmentation is essentially a technique to artificially increase the diversity and the size of the data set by creating modified versions of the training samples. So essentially if we had training samples as x1 comma y1, x2 comma y2 and so on, essentially we would using data augmentation create a diverse set of x1 samples itself, right. Now the goal is essentially to help the models generalize better by exposing them to the variations, right. We know that the training data and the test data may have some difference in their appearance or in their basic distributions. Now data augmentation is a good way to try to connect the training data to the test data. Essentially what we are trying to do is we are trying to augment and create a diverse training set in such a way that the model does not get affected to the distribution shift in the test set, right. Now essentially there are two augmentation techniques, but there are more sophisticated augmentations which do not fall only in these two criteria, right. So first is the geometric augmentation, which is essentially rotation, translation, scaling, cropping, affine, transformation, etc. The second one is essentially the photometric augmentations. Photometric augmentations such as contrast, brightness, Gaussian noise, blur, color jitter and so on. Now again there are certain augmentations that do not fall into these two categories, and they are more sophisticated augmentations either combining both of them. But again these are the broad categories of augmentations. Now let us take an example and look into some of these augmentations, right. Now photometric augmentations is essentially trying to understand or improve the appearance part of it. So if we have an image, if we train the model using different style or different appearance, it may become robust to that particular feature. Geometric transformation try to improve the spatial invariance, right. So if we have an image and if we can maybe rotate it or train it in those spatial varying scenarios, maybe it gets trained for those scenarios as well, right. Now let us go over certain data augmentation techniques. Let us start with the random rotation, which is essentially just rotating the image in a different angle. So we have this, which is the original image, but we can rotate the image with say a probability of 0.5, and for each probability it could have a different type of rotation, right. Now let us take a look at random crop. Random crop also tries to crop an image at random locations. Once it takes a crop, it makes it full scale. So essentially if we take a crop of the image, we would essentially make it match the dimension of the input, and that would be the augmented sample, right. Similarly, we have random invert, which is essentially inverting the colors of a given image. We can observe this in some of these samples. There is random solarize, which is essentially it solarizes the image by inverting the pixel values. Some of the examples can be seen here. And lastly, we have random vertical flip, which essentially flips the image again with a probability. Now, data augmentation essentially are used with a probability. So, they could be used with a probability of 1, which is use them always. They could be used with a probability of 0, which is never use them, or they could be used with a probability which lies somewhere in the middle, let us say for example 0.5, right. So, 0.5 probability that the augmentation would be applied to the training sample, and once it is applied it would be passed to the model. Okay. Now, some other data augmentation techniques are say 5 crop, which is essentially cropping the given image and then breaking the image into 4 corners and the central patch. So, we have the original image, we would take all the 4 corners inside this image and the central patch and then return these patches. We also have augmentations like color jitter, which is essentially randomly changing the brightness, saturation and other properties. Some of the examples can be seen here, where we have the original image and then we have other images which are after the color jitter transform. There is also random perspective transform, which is essentially trying to change the perspective of an image, right. So, the image is viewed in a particular manner. The change in perspective is essentially changing the viewing angle and changing the image, and then whatever is left is added with pixel of value zeros, right. Now, data augmentation techniques, if we focus more on the geometric augmentations, geometric augmentations could be helpful when the target domain essentially has different camera viewing angles, different object orientation, different scale and so on. Now, certain scenarios or certain common scenarios could be say drone imagery, where the camera angle keeps changing. We have autonomous driving, right. There are certain aspects which is essentially in robotics, where the pose and the perspective keeps changing, and if the training data doesn't have samples for these changes of common scenarios, which is changing in perspective and so on, data augmentation techniques could be used to augment the training samples. For photometric augmentations, essentially it could be used when the target domain has different illumination condition, different weather condition, different sensor noise, different types of blur and so on. Now, certain common criteria are when in outdoor robotics there is an ever changing environment, what would happen then. It could also be used for different types of modalities. For example, if you are training on RGB and going to other modalities, even then photometric augmentation could be used. Now, these augmentations could be used to improve the performance. However, again it depends on the target domain as well. There could be scenarios where the target domain is too hard to replicate using these augmentations, and in those scenarios the augmentations may not be used, right. Okay. Now, let us take a look at the classification datasets, essentially datasets which are used for classification task. Let us look at ImageNet dataset, right. This ImageNet dataset is essentially a large scale dataset with 1000 classes. Now, ImageNet dataset is something that we will discuss, which is essentially discussing the development of various CNN backbones, right. And this was done keeping ImageNet dataset in mind, because they were trying to compete in a competition which used the ImageNet dataset, right. A lot of these backbones now are trained on ImageNet and other datasets also. So, these are backbones which have some pre-training knowledge of some of these datasets, right. Now, other datasets include CIFAR 10, CIFAR 100, MNIST and Fashion MNIST, right. Now, an example of CIFAR 10 dataset is essentially given here. Now, in CIFAR 10 dataset, the image resolution is 32 cross 32. Essentially what it means is the height and the width is 32 cross 32. Since it is an RGB image, it will have 3 channels, which is RGB. So, the number of channels is 3, right. So, whenever we look at these type of information, we know how to interpret this, right. Okay. There are 10 object classes and there are about 60,000 total samples, right. Some samples from the dataset can be observed here, which is essentially from classes like plane, car, bird, cat, deer, etc. right. Now the first slide where we discuss the classification operation, these are some of the input images that could be used in that particular example. Essentially the input image could be an image of a plane and we can use that to train the model, right. Okay. Now some other datasets for classification tasks are datasets like Caltech 101, Food 101, Oxford IIIT PET dataset, and again the Stanford cars. An example of Stanford cars is given here, which is some of the sample images. Now one interesting part is there may be datasets with a variable resolution of the images. For example, in Stanford car dataset the resolution varies from 360 into 240 to 512 in 4, right. So the input or the training data or the dataset itself does not have a fixed resolution, it has a variable resolution, right. Okay. Now again these are color images, the number of objects could be very high, right, and there are around 16,000 training samples, right. Now let us take a look at classification datasets for aerial imagery. Now there are certain datasets, for example the UC MERS land use datasets, which is essentially trying to classify different type of land classes into 21 classes. There are also datasets like Eurosat, which is essentially the satellite land cover dataset, which is using the Sentinel-2 imagery, right. Let us take an example here. This example is from the MAVOC dataset. Now MAVOC dataset essentially was introduced as part of the entire 2021 PVVS challenge. This challenge was hosted by CVP in CVPR workshop, right. Apologies for that. In CVPR workshop, right. Now the task is the automatic target recognition task, which is essentially a classification task, right. So the task is there are two modalities, which is RGB or electro-optical, or SAR, which is given, which we can observe in the image, right. Now the task is for certain objects its corresponding labels are given, right. So there is the car with a corresponding label, there is a truck with a corresponding label, and so on, right. The task is essentially a recognition task. We have these different types of cars and trucks, can we classify them accordingly, right. Now we can observe that for RGB it seems to be intuitive, right. However, if we look at the SAR images, we observe that they are very noisy, right. Now essentially classification on SAR imagery would be pretty difficult. Again, the image resolution of the EO or the electro-optical data or electro-optical modality is 31 cross 31. The image resolution of SAR is 55 cross 55. Okay. Now one gentle advice would be to participate in these challenges. So after this course, after we have introduced basic concepts, and after you are comfortable with Pytorch or MATLAB or any other framework that you feel is very intuitive to you, CVPR or ICCV or these conferences regularly host challenges, and one advice would be to participate in these challenges, because you would be able to learn or you would be able to come up with different types of solutions and strategies which are not too intuitive, but you would essentially you do a lot of experiments and come up with these strategies, right. And that would be within a time crunch. So that would be within a month, or let us say 2 weeks or 3 weeks, right. So this is essentially where you would develop a skill, a very strong skill to implement deep learning models and to quickly improve its performance, right, either using very sophisticated techniques or using very basic and heuristic based techniques, right. Hence the advice or the request would be to participate in challenges. Okay. Now let us look at Pytorch. Now in the previous tutorial we had very quickly or very briefly reviewed the AutoGrad facility or the AutoGrad functionality in Pytorch. Now let us look at the basic structure of Pytorch and let us go into training a model, right. Now the first part essentially focuses on dataset loading and dataset pre-processing. This is essentially when we have a dataset, we want to separate it maybe into train and test set. Once we have done that, we want to define the data loader that would iterate over the whole data set and so on, right. These are steps that we will see in the subsequent slides. Then it focuses on the next part, which is defining the model, right, and we will define either a very small model, say 2 convolution layers and 2 fully connected layers and so on, or else we would define sophisticated models or maybe borrow architectures like ResNet and VGG and build up upon those architectures, right. But whichever model we use, we need to define the model, we need to define the loss function and the optimizer, and essentially focus on the training and then focusing on the evaluation. Now there are important concepts in Pytorch, but again deep learning frameworks in structure are very similar. So these concepts also would be very similar in other frameworks, however their syntax and all would be specific to the framework. So dataset and data loader is a component which is very important in Pytorch. In this particular session we will focus on generic or mainstream datasets. When I say mainstream, it is essentially Pytorch has a facility for us to directly import it, right. So we do not have to write a custom dataset and data loader, etc. But yes, if you are working on datasets that you are creating, you would essentially need to write a data loader on your own. But for this particular tutorial, we will focus more on the generic datasets. There is nn.module, which is essentially the class which defines all the neural network operators, and we would essentially use this as a base class and derive our model out of this base class. There is the forward pass, which is essentially passing the input and getting the output. There is the backward propagation, which is updating the weights and essentially the optimization step itself, right. So let's start. The first step in the workflow is essentially importing all the necessary libraries. This seems to be a very simple step, but yes, there are a lot of errors when it comes to importing necessary libraries. So always remember, whatever functionality or whatever frameworks you are using, always import all the libraries. We do not want to get stuck in importing the libraries, right. The second part is loading the dataset. Essentially loading the dataset is trying to define the train and test set, import it, and then use the data loader to iterate over the whole dataset, right. And then it is to define the model, essentially build the model using the nn.module functionality, right. Now we have two approaches. We can either train the model which is trained from scratch, but we will see that that's not the best approach, because it is better to take a model which is pre-trained and then use it for our particular task. And the second part is we can either use these models which are pre-trained and then use it, right. But in both cases we do need to define the model, right. Now the next step is essentially training the deep neural network, which is optimizing the loss function, right. Each task has its specific loss. Since we are focusing on classification, we are focusing on losses like cross entropy or mean square error. However, for segmentation we would have a different set of losses, right. So again, it depends on the class. However, the philosophy of training the deep learning network remains the same. Essentially what we are trying to do, or what the framework is helping us do, is once we define the error, it is trying to minimize this error and give us the best optimal set of weights. When we have theta star, which is essentially the best optimal set of weights, we save this as a model checkpoint. Model checkpoint is essentially just saving these set of weights, right. Once we have these set of weights, we will use it for our inference. Okay, let's get started. This essentially is just a photo of importing all the necessary libraries, right. Now essentially we can see that there are libraries like OS, Torch, NumPy, Pandas, TQDM, right, and essentially focusing more on more sophisticated parts as well, right. Now essentially yes, importing the libraries is a very preliminary and an important step. Okay, now let's take a look at how we can load the dataset, right. Now whenever we have a dataset, essentially our goal is to focus on the train set and the test set. Now if it is mainstream datasets, the datasets that we discussed in the previous slides, they already have a train, test and even a val set which is defined, right. So, when we are training deep learning models, we focus more on the predefined train and test set, right. Now, the goal is essentially the data set has images and its corresponding labels. We want to import these images and then depending upon it use different type of data augmentation techniques or essentially different type of transformations. When we say transformations, it is essentially the data augmentation technique, right. Now, let us take an example of the dataset class. Since we are working with fashion MNIST, which is a generic dataset, right. It is a mainstream dataset that even Pytorch essentially has the facility for us to load directly. We use datasets. Datasets essentially comes from Torch Vision. So, if we use the command from Torch Vision import datasets, we essentially can use this datasets command. If we use the datasets command, using this we can essentially directly get the training data, right. So, training data is given as datasets.fashionMNIST. Root is essentially where the dataset from Pytorch will be saved inside the particular local system. Train true is essentially using the train true, download true and transform. Transform is essentially different data augmentation techniques followed by 2 tensor. Now, why do we need 2 tensor? It is because whenever we have an image could be either in a PIL or some other format, right. So, it is in an image format, right. We need to convert this into a tensor format, right. For this we use 2 tensor. Now, once we have defined the train data, we also define the variable which is test data in a very similar manner, right. When we put train as fall, it essentially means it is focusing on the test set, right. Now, we can use different type of dataset transformation techniques and we can essentially either use a custom transformation or we could use some transformation like color jitter, vertical flip and so on. So, essentially we could use different types of transformation in this particular part as well, right. Now, since we have these variables defined which is train data and test data, now let us move to the second part, which is once we have defined the data set, once we have defined the train data and we have defined the test data, now we need to use something known as a data loader. Data loader essentially is an iterable tool which will iterate over the whole data set, right. For example, if I have a train data, what the data loader would do is it would break this train data into different chunks and it would use different chunks for each iteration. So, essentially break this data into different components which we will define as batch size, and from each batch size take that particular chunk, give it to the model, train the model, update the weights and then so on, right. One more important point here is that whenever the data loader is used as an iterable tool, it creates the set of these batch size or these sets, and the way it is sampled is always mutually exclusive. It would never be that I use the first set and for the other iteration I would again use the first set, it would never happen. So, you create a chunk from the training set and randomly you can keep training different chunks, right, but it would never repeat that particular chunk. When I say chunk, it is essentially the batch size, right. Now, let us go over the data loader. Data loader essentially takes the training data which we defined in the previous slide. We define the batch size which is 64 and we say shuffle as true, which is shuffling, which would essentially after each iteration it would shuffle the data. Now, this is the train data, similarly there could be a test data. So, train data loader is essentially iterating over the training data using data loader. Test data loader is essentially using the data loader with the test data, right. These are variables we have defined. Now, these are again batch size, iteration and epoch is something that we have seen in the lecture itself, right. So, we will not define it here, but intuitively you must understand the basic nomenclature when we say it is a batch size versus when it finishes an iteration and when it finishes an epoch, right. Now, let us focus on the torch.nn module. This module is essentially very important, and this is why we use the frameworks, right? Because instead of us defining various operators like convolution, activation, max pooling, etc., the deep learning frameworks have these base classes which essentially define neural network modules, and these modules then work with CUDA, which is deploying these tensors, performing all these operations on GPU itself, right. Now, whenever we define any model, it is essentially a subclass of this class itself, right. What do I mean by that? Now, we import torch.nn as nn, which is very important, and we import torch.nn.functional as f. Both of them are very important, and essentially one recommendation would be you should go to the Pytorch official documentation and you should essentially read what are these import statements, right. That would give you a much better clarity, right. Okay. Now, what we want to do is we want to define a class model which is our model, right. Our model is essentially building up upon nn.module, which is the parent class or the base class, right. Now, once we do that, we define convolution 1, which is self.con1, which is essentially nn.con2d with arguments 125, followed by self.conv2, which is nn.con2d 2025, right. Once we have defined these two layers, we can define the forward, right. Forward, once we define, it is essentially taken with self and x. X is the input that would come to the model. Now, x is given as f.relu of self.conv1x, and essentially we return the value of f.relu of self.conv2x, right. Now, let us see what it means, right. When we first look at self.conv1, it is essentially using nn.conv2d 125. Now, what does this mean? It means when we say 1, it is essentially defining the in channels. When we say 20, it is essentially defining the out channels, and when we say 5, it is essentially the kernel size. Now, in convolution, we do understand the meaning of in channel, out channel and kernel size, right. Okay. Now, let us look at the second part, which is forward. What does forward mean, right. Now, we will go back to the diagram that we have been using, which is an oversimplification of these architectures, but it helps us to give understanding. Now, the input image essentially is x, right. Now, x would pass through conv1 and then it would pass through conv2 and so on. It does not mention, like it only mentions return here. So, we will essentially only return this value, right. Now, what is happening is when I say x is equals to f.relu self.conv1 of x, essentially I am taking x, which is the input image, I am passing it through the convolution operation, I am passing it then to the ReLU, and then I get x, which is the feature map. So, x here is the input, x here is the feature map after these set of operations. Now, this feature map again is passed through conv2 and ReLU and then is returned, which is essentially this part, right. So, a intuitive way to understand is we should define all the layers that are useful in the model in the init itself, right, which is defining different convolution operation, different fully connected layers and so on. The forward essentially defines the forward pass. It is essentially defining how the model is going and when it is returning the value, right. Okay. Now, let us look at the optimization loop. Optimization loop is essentially the train and the optimization model within, right. Now, if we look at this particular code, we can see that we have defined a loss function, a corresponding optimizer, right. Once we have defined the optimizer for let us say 10 epochs, we run through a loop. In this loop, we have a train loop and a test loop, right. Now, in the train loop, we are using the train data loader, we are using the model itself, we are using the loss to define the loss and we are using an optimizer to optimize the model weights. When we go to the test set, essentially we focus on the test data loader, we focus on the model, and we may want to print the loss, so we will print the loss. But we do not need an optimizer here because we are not training, we are just taking the weights theta, finding theta star and then using it in the test loop. Okay, let us take a look at the train loop. In the train loop, essentially we have model.train, which is an essential point or essential step. From model.train we have a for loop. In this particular for loop, for a given x and y, which would iterate over the whole data loader. For a given x, y, which is input output for which would iterate over the whole data loader, we would have prediction, which is the output of a particular input to the model. We would define the loss. Once we have the loss, we would essentially back propagate and update the model. Now let us see what each of these code mean. Now when we say model.train, it is essentially useful because it adjusts some of the layers which behave differently during model train and model inference. If you remember, there are operations like dropout, there are operations like batch normalization. These layers have a different functionality during training and they have a different functionality during test, right? And hence when we define model.train, it sets these parameters in the train mode. Once we have done that, we define the loss function to compute the loss. Once we have computed the loss, we use loss.backward. When we use loss.backward, it is essentially to compute the change in weights, which is delta x. Currently in this particular, let us take delta w. Delta w essentially is computed using loss.backward. Once we have computed loss.backward, we use optimizer.step. Optimizer.step essentially updates all the weights, right? Now once this is done, then we set the gradient of all the weights as 0, which is essentially optimizer.0grad. It clears all the gradients, right? Okay. Now in the test loop we have other operations that we can use, for example model.eval, right? We have operations like torch, no grad. Now model.eval is similar to model.train, it updates the operators to behave differently during inference. So we know that dropout and batch norm would now behave differently, right? Now when we say torch.nograd, it is essentially not to compute any gradients in that particular step. So if we see in this particular step, no gradients would be computed. Essentially we would have an output prediction, we would compute the loss and then we would compute the last part, which is the correct, right? And we will come back to this particular statement in the subsequent slide. Okay. Now let us go over essentially to run a Pytorch model on, it is essentially to run a deep learning model using Pytorch framework on the MNIST dataset, right? Now the first step, as we saw, is to import all the necessary libraries, alright, and this is something which seems very trivial, but I know a lot of people who, including me, who keep making mistakes. So never forget to import all the necessary libraries. The second set of commands is essentially to check if the code is working on a CPU or on a GPU, right? Okay. Now the second step that we observe here is defining all the hyperparameters, batch size, test batch size, epochs, learning rate, momentum and all is set here, right? Once this is set, we focus on the data loaders, right? Data loaders is essentially, we first define all the transforms, which is something that we saw. We can define two tensor, which is essentially, it essentially converts a PIL or a NumPy to a tensor, right? Now once this is done, we can also work with different type of transformation and data augmentation that we saw earlier, but for now we are keeping it simple and just using the two tensor. Now we define the train data, which is essentially the train set of MNIST. We define the test data, which is essentially the test set of MNIST. So for this, train is false. We define the train underscore loader, which is the data loader which iterates over train data. So we can see that train data is defined above, and we are using that in the data loader as an iterable tool. We define the batch size, right, similar to the test loader, right. Now let's define the model. Now this model is different than the model we saw in the previous slide, right, but essentially we do understand how to define the model. Now we define class net, which is the name of the model, name of the class. It builds up upon nn.module, right. We have an init which defines or it initializes all the various layers that are useful for this model. So we define self.conv1, which is the convolution layer, self.conv2, which is again the second convolution layer, followed by a dropout layer. Now once the convolution layers have ended, we need a fully connected layer for the task of classification, which is why we define the fully connected layer self.fc1, which is the nn.linear layer. nn.linear layer is essentially the fully connected layer. And then we have the fc2, right. Now one thing to observe here is that the output is 10 because there are 10 classes in MNIST. Now when we define the forward, essentially we will define the forward pass, right, the forward flow of the input. So the first X that we see is the input. Now this input has been updated following the conv1, maxpool and ReLU operation. Now this is essentially a feature map. Now this is passed throughout the whole model, right. Once we pass it through the whole model, we take a softmax. Softmax is essentially to convert the output into a probability distribution, right. Now we have model, which is essentially net, right. Now model, this command which is model is equals to net bracket dot to device is essentially pushing this model into the device, which is our GPU, right. We have an optimizer which is defined here. Now let's focus on the train loop. In the train loop, we essentially define model as train. Once we have defined model as train, we have something which is very similar, right. If you look at the first command, it is essentially taking the index, the data which is the input image, the target which is the label, and it will enumerate across the whole train loader, right. It would define these values, which is essentially get the input image and target. We would make all the gradients as 0. We would get the output, get the loss, and finally we would do loss dot backward and optimizer dot step, right. Now essentially once this is done, we would run the test, right. Now in the test loop, it follows a very similar operation that we saw earlier, right, and we will come back to this part in the subsequent slide, right. But overall the test loop is similar to how we saw in even our slides, right. Now if I run this code, which is essentially for the defined epochs, we will run the train and the test loop, which follows a very similar structure as we observed even in our slides, right. It is not the same, but it follows the similar template, and that is what is important, right. Now once we start training this model, we observe that it is essentially using a CPU. Now this can be changed depending upon Pytorch and all, but since it is a very simple model, we have deployed it on CPU. Convolution 1, convolution 2, dropout, fully connected 1, fully connected 2, and we can see that it starts training, right. So we can see that the model for first epoch has these many iterations. For each iteration we plot the loss. After the loss is plotted, on the test set we can observe that this is the loss and this is the particular accuracy, right. Now observe in the end of epoch 1 the loss, which is 0.54, and as we keep training, say for a different set of epochs, let us say for epoch 8, we observe that the loss is very high, right, and hence we know that the accuracy for the, we know that the model has been trained properly on the train set. However, we should also observe its performance on the test set. So, on the test set the average loss is 0.0572 and the accuracy is 98%. We can keep training it for 10 iterations or we can stop it depending upon the convergence criteria that we have discussed, right. Now, let us get slightly different model definition compared to what we saw, but the fundamentals remain the same. We can actually understand what self.con1 would do, similarly for self.con2, right. Now, if we observe the forward pass, we essentially see that after passing through the convolution layers, there is this particular operation which is x is equals to x dot view minus 1 320, right. This is essentially the flatten operation. Now, once we have convolution layers, the feature map needs to be flattened and then passed into the fully connected layers. Now, we perform x dot view of minus 1 320. Why 320? 320 is because the input to the first fully connected layer expects an in channel of 320, right, and hence we make it as 320. So, when we say x is equals to x dot view minus 1 of 320, it is essentially taking a tensor, reshaping it in such a manner that the one output or one dimension is 320, the other dimension can be adjusted accordingly, it does not matter, right. This is what Pytorch, or this is what the code is telling the model, this is what is being done. Now, if you again observe FC2, the output of FC2 is 10 because of 10 output classes, and finally we pass it through softmax. Now, an interesting part is once we finish the backbones lecture, we would be able to define the dimensions of feature maps at various levels. We would also be able to calculate the number of learnable parameters, right. So, essentially if we have a model definition given to us for at least a class for the task of classification, we can comfortably answer a lot of these questions, right. Now, let us take the look at test loop, which is essentially the last part of the lecture. We define model eval, which is essentially modifying the operators to come into the evaluation mode, which is dropout and batch norm. For torch no grad, which is not to compute any gradients in the subsequent slides in the subsequent steps, we unpack data and target. Data is essentially an image from the MNIST data set, target is essentially the label, it could be 0 to 9, right. Now, when we print the output, which is output dot shape, it will essentially give us the shape of the output tensor and we can essentially compare it with the output prediction. Now, let us quickly take a look at this part, right. Now, ground truth, the dimension was batch size comma 1, the prediction output was batch size comma n, n is the number of classes, right. Now, when we perform an argmax operation, which is argmax across dimension 1, we have, now if we look at prediction, batch size is in axis of 0 and the n is at an axis of 1. When we take an argmax across this particular axis, our resultant tensor is 1, right. Now, what is happening when we are doing an argmax operation? Essentially, let us assume for now that our batch size or the batch size we observe, okay, let us assume for now the batch size is 4. When I say batch size is 4, it is essentially 4 samples which are taken, right. So, sample I would say B1, B2, B1, B2, B3, B4. Now, this is the batch which is the number of samples. Now, n is the number of classes which is essentially from 0 to 10 classes, right. Now when we take argmax, what is happening is across this particular axis, which is across the n axis, we are trying to calculate the element which is the highest in value, right. So let us say batch 1 was essentially the 9th class, right. Now when I do an argmax, it would return 9 to me. Similarly, if I see batch size, batch sample B2 is of the first class, then it would return 0 to me, and so on, right. Essentially it is returning the element with the highest probability, which is what we want, right, because essentially the highest probability corresponds to the sample being predicted to that class. Once we have this, which is essentially batch cross comma 1, now we compare it with the ground truth. When we compare it with the ground truth, and when we focus on an operation like predicted dot equal to, it compares the ground truth and the predicted value and gives us a Boolean map or a Boolean vector. Now in case the ground truth is correct, it would give us a value of true. In case the ground truth is not correct, it would give us a value of false, right. Since our batch size is 4, we would have 4 entries. Now when we say dot sum, it is essentially giving us a sum of all the true values here, right. This essentially means the number of true samples in that, or the number of samples with correct classification in that particular batch, right. And this is iterated over and over again. Once we iterate this, we have the number of correct samples predicted across the whole test set. Once we have the number of samples correctly predicted, we essentially calculate the test accuracy, which is the number of corrected samples across the number of corrected samples upon the total number of samples in the test set, right. This is essentially how the operation is working. Okay. To summarize this particular tutorial, also quickly review different data augmentation techniques. We saw how data augmentation techniques could be used to increase the diversity, right. We did a brief review of different data sets for classification task. Essentially we went over data sets which are used in a generic manner like ImageNet, Cypher10, MNIST and so on. We also saw certain data sets which are specific to aerial imagery. Lastly, we saw a code demo where we tried to use the different fundamentals that we reviewed on Pytorch. We saw its working in Google Colab. We saw how the loss, once it starts training, converges to a certain value, decreases in its magnitude. And we also saw how for classification task the accuracy computed. Thank you.